Please pause the video, read the problem, and attempt to solve it yourself first. Okay, in this problem, as you have read that, we are asked to find the least material. And basically, this is an optimization problem because in optimization problem, we are asked to find the best and or worst kind of scenarios, the least amount of material or the most amount of material. These type of questions are optimization. And in any optimization problem, having a visualization would help a lot. So let's begin with that. So we are given that we have a square-based box. So I just draw that here. Square, and the height of that can be anything. I just know the base of that is a square, so the length and the width of the base are same. So for example, I say they are x. And the height of that can be anything like h. And what we are given is it's supposed to hold the volume of 200. So we know the volume of that is 200. So x squared times h, which is length times width times height, which is x times h, is supposed to be equal to 200. So this is the volume. And we want to figure out what makes the amount of material the smallest, the least amount of material. So that is our objective. We want to minimize the amount of material used. And based on the description in the problem, we know that the sides of this box, we only have one layer of cardboard, but the top and the bottom, there are two layers of them. So let's see how much material we have in total. So for the base, the material is supposed to go to the area of that. This is the cardboard. So the amount of that would be the area of the base, which is x times x or x squared. But because it is two layers of that, we have 2x squared. So 2x squared, this is for base. For top, we have the same thing, 2x squared. And for the sides, we have 4 sides here. So on each side, we have one rectangle. So let me just show that here. So for example, this is one rectangle here, and we have 4 of these, which adds up to x times h, which is one of them. We have 4 of them, so it's 4xh. So this would be the side. Let me just fiddle it here. Perfect. So overall material, the whole material that we are going to use is a summation of these all numbers. So the amount of material, so I just call that m equal to 2x squared plus 2x squared plus 4x times h, which let's simplify that. 2x squared plus 2x squared adds up to 4x squared plus 4xh. And we want to minimize these. This is our objective, and to minimize the objective function, we simply take the derivative of that. We set that equal to 0 to find the critical points. So to take the derivative of this, there is a little bit of an issue that we have more than one variable. We have x and h. And this is not a multivariable function because x and h are not independent. They are dependent on each other. Why? Because we have another equation which is that x squared h is equal to 200. This is called constraint. Maybe I can say, for example, x is equal to 5. But h would be kind of dictated to me, or I can say x is equal to 100. Then h would be kind of dictated to me that h has I have very little height for that box. So x and h are kind of dependent on each other. That's why we have a constraint. From constraint, I can try to solve for h, because as I said, x and h are dependent on each other. So I can say h is equal to, for example, 200 over x squared. You have an option to solve for x as well, but that would be a longer process because first of all here you need to take this square root, and here there are a bunch of spots that you need to replace them. But here h is the easiest. Now that I know h is equal to 200 over x squared, I can plug that into my material function, my objective function. And it helps me to reduce the number of variables. So I have material is equal to 4x squared plus 4x times h, which in this case is 200 over x squared, which simplify that 4x squared. I have 1x here, 1x squared here. I can simplify that. So I only get x, just single x in the denominator. And I have 4 and 200, which they get multiplied to 800. So overall, I have material is equal to 4x squared plus 800 over x. This is my objective function, and it is function of only one variable right now, which is perfect for optimization. So I simply take the derivative of that with respect to my only variable. I can just use m prime to indicate the derivative, and that single variable is just x. So I take the derivative with respect to x, it would be 8x plus the derivative of that. So let's just, before taking the derivative, write that a little bit easier, like 800 times x to the power of -1, because right now it's in the denominator and the power of that is 1. I just take it to the numerator and the power would be -1. And the reason that I did that is I avoid using quotient rule. Right now I only have power rule. So I have 8x plus 800 with a -1 x to the power of -2. So let's simplify that a little bit. So m prime is equal to 8x plus, I have 800 times -1, which basically makes it -800. And I have x to the power of -2, which is basically 1 over x squared. Don't forget that negative power only means it's a reciprocal. It is in the denominator. Okay, perfect. Now I have this. And I simply set that equal to 0 to find the critical point. So now that I know 8x minus 800 over x squared is equal to 0, basically I just multiply the 800 by 1 here. I can move this negative part here to the other side. So I can write 8x is equal to 800 over x squared and multiply both sides by x squared. So I get 8x cubed is equal to 800. So I'm just multiplying both sides by the denominator. So I'm getting rid of that denominator. So I have 8x cubed. I have 1x here times x squared is x cubed. And here the x squared would get cancelled. So it's equal to 800, dividing both sides by 8. These two get cancelled. This would cancel to just 100. So overall, I have x cubed is equal to 100. So x is equal to third root of 100. So this is amount of, not amount of material. This is the length of the base, which optimizes the amount of material we need. And let's see what we are asked. Find the dimensions. So we need the dimensions, which means length, width, and the height. So because the base is a square, I can just say that, okay, the base, kind of the lengths and the widths of the base, which are same, both of them are third root of 100. How about the height? Okay, the height, which I already have that through the constraint, is equal to 200 over x squared. So I can just simply write that as 200 over third root of 100 squared, which is already perfect. I can simplify that, but it is already good enough. Take a few moments to read through the question carefully and give it a try before watching the solution. Okay, in this question, we are asked to find the fifth order Maclaurin polynomial of this given function first, and then evaluate the fifth derivative of that function at x equal to 0. This is a notation for fifth derivative. Okay, so first we want to find the fifth degree Maclaurin polynomial or fifth order. One way would be just writing the general format of that. Let's just write the general form. So I can say T5. Because it's Maclaurin series, Maclaurin polynomial, it's basically Taylor series centered at 0 or about 0. So I can say T5 of x is equal to the function value at 0. I just write at x equal to 0, so to make it exactly Maclaurin series, because Taylor series generally is at x equal to a, very general form, but Maclaurin series is at 0. It's f of 0 plus f prime of 0 x to the power of 1 plus f double prime of 0 over 2 factorial x squared plus f triple prime of 0 times x to the power of 3. The fourth derivative at 0, 4 factorial x to the power of 4, and the fifth derivative at 0, 5 factorial x to the power of 5. So we want to write these, but if you want to take the derivative of these 5 times or 4 times, it's a very, very long procedure, because right now what we have is sine of 4x times e to the power of 2x squared, which we need product rule. And for this part, we need a chain rule. And the next time you need 3 terms for product rules. That's a very, very long process to just get to f double prime. F triple prime, the fourth derivative and the fifth derivative, that would be really a painful process, a very long process. So what we would do instead is writing the Taylor polynomial at 0 for sine of 4x separately, and for e to the power of 2x squared separately. E to the power of 2x squared separately. So let's do them separately. But how? I mean, taking the derivative of these also 5 times, it's not a very simple process. Maybe for sine it's a little bit easier, because sine is cos is negative sine. It's going back and forth very simply. But it's still not a very quick process. Instead of that, we need to have a little bit of background. So you have 5 famous functions: sine of x, cos of x, e to the x, ln of 1 plus x, and 1 over 1 minus x. We need to memorize these 5 functions and their Taylor series at 0, or their Maclaurin series, Maclaurin polynomial. So what we know that sine of x at x equal to 0 is approximately, I just write the equal sign for now, is equal to x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial, and so on. But we don't need to go all the way, because we need to just go up to the point that the power would be 5, because we are asked for the fifth, or T5, fifth degree. So right now this is for sine of x. What I need is sine of 4x. So simply instead of x, I plug in 4x. So it would be 4x minus 4x entirely cubed. Make sure that the 4 also is cubed, over 3 factorial plus 4x to the power of 5 over 5 factorial. And I don't need to go further, because the power of x right now is already 5. So I can just stop here and I say, okay, the T5 would be this. So this would be the T5 for the sine of 4x. Let me just write it this way. This is a T5 for sine of 4x. And it's not very formal way of writing that, but it kind of does the job. We understand what we are doing. For e to the 2x squared, we have the same thing. E to the x is a famous function, which we already should have the Taylor series at 0 memorized, which is 1 plus x squared over 2 factorial plus x to the power of 3 over 3 factorial plus x to the power of 4 over 4 factorial, and so on. But again, this is for e to the x. What we want is e to the power of 2x squared. So I simply replace all the x's with 2x squared. It would be 1 plus 2x squared plus 2x squared over 2 factorial plus 2x squared cubed over 3 factorial, and lots of other terms, which we don't need any of them. I know that I didn't substitute 2x squared for these x's, but because we are looking for x for t5 for the fifth order Maclaurin polynomial, we need only to go up to the degree 5, up to the point that the power of x is 5. So the power of x here is, this is x squared, which is x to the 4. Here it's x squared cubed, which is x to the 6 overall. So actually, we don't need this one neither. We just stop here. So I can just write that this way, that the t5 for e to the power of 2x squared is equal to 1 plus 2x squared plus 2x squared over 2 factorial. Nothing more. Now that we have each of them, the t5 for each of them separately, we can just multiply them by each other. We can FOIL these two. So let's just, before doing so, I simplify each of them. So this one would be equal to 4x. I have 4x entirely cubed. So it's minus, so because the 4x is entirely cubed, the 4 is also cubed, x is separately cubed, over 3 factorial, which if you have it memorized, it would be just, if you can just quickly evaluate that, I mean, you don't need to memorize that. It's 3 times 2 times 1, which is 6. It's okay, just, or you can just simply leave it at 3 factorial, plus the next one, which is 4 to the power of 5, x to the power of 5 over 5 factorial. And this one would be 1 plus 2x squared. It doesn't have any power, plus, again here, the power of 2 would be also 2. The power of x squared would be 2, which adds up kind of 2 times 2 is 4, x to the 4 over 2 factorial. So this would be the Taylor polynomial for each of them at 0. So for the whole function, you can just write the t5, but before that, let me just multiply them. 4x minus 4 cubed x to the power of 3 over 3 factorial plus 4 to the power of 5 x to the power of 5 over 5 factorial. This is for sine of 4x. I multiply that by 1 plus 2x squared plus 2 squared x to the power of 4 over 2 factorial. Now we just FOIL these two. So this is for sine of 4x, and this is for e to the power of 2x squared. When we FOIL them, so let's just multiply these 4x by this bracket. We get 4x plus 4x by this one gives us 8x cubed. 4x by the last one gives us 4 times 2 squared times x to the 4, which is adds up to x to the 5 over 2 factorial. And now the next one, we multiply these by these, which makes it negative 4 cubed x to the power of 3 over 3 factorial. These times these, which makes it minus 4 cubed. There is 1, 2 here, and the x's would adds up to x to the power of 5 over 3 factorial. And this one times the last one. These two, when I multiply these two, the power of x would be x to the power of 7, which I don't need that because again, I'm just looking for t5. I only go up to power of 5. So whatever combination of these two brackets, when I'm foiling them, adds up, the power of x adds up to more than 5, like 6, 7, or above, I do not include that. So these two, okay, it adds up to x to 7. I don't need that. These two, it's x to the power of 5, so I can do that as well. So I have 4 to the power of 5, x to the power of 5 over 5 factorial. And these two makes the power 7. These two makes the power 9. Okay, so I don't need that. So I just stop here. This is the t5 for the function f of x. So this is already the answer. If you want to make it a little bit better looking, it's better to have that in a factored form. How? Not factoring every terms from the whole thing. Just factoring the x here. I mean, just kind of collecting the x to the power of 1s with each other, x to the power of 2 with each other, x to the power of 3 with each other. So here I have just 4x. There's only one term with the power x to the power of 1. This one, I have only one term with the power of, no, I have two terms. I have this one, which the power of x is 3, and this one, which the power of x is 3. So I just write x cubed multiplied by the coefficients, which is 8 minus 4 cubed over 3 factorial. It's kind of some, I'm just factoring the x cubed out. And to make it kind of a little bit conventional looking, I just put the x cubed after the bracket. And this term, this term, and this term, these three terms, they have x to the 5. So I take out x to the 5 out. So I just write it after the bracket. The first one would be 4 times 2 squared over 5 factorial. So when I take out the x to the 5 out, this is the remaining. When I take the x to the 5 out, this would be what is left here, which is minus 4 to the power of 3 times 2 over 3 factorial. Let me just make it a little bit to the right. And from the last one, I have this thing, which is positive. Positive 4 to the power of 5 over 5 factorial. This is a little bit better looking. In red. Yeah, this is a little bit better looking for T5. This is what we want for the first part of the question. And now in the second part, they are asking, what is the fifth derivative of the function at 0? Do we need to take the derivative 5 times? Not really. Because we already have T5, we can answer questions like, what's the first derivative, what's the second derivative, third, fourth, and fifth derivative? We can answer up to the fifth derivative by just having the T5. How? You remember that I said, okay, this is already the T5. Let me just copy paste that. This is the hard way to get the same thing. These and these are exactly the same way. Just we did that through the kind of a little bit shorter way by just having that background knowledge of e to the x and sine of x. Now that we know these two are same, we can basically set them equal to each other. And why we are doing that, I mean, you will see that quickly, that these two are equal to each other, and I'm looking for the fifth derivative. So I'm looking for what? The fifth derivative of the function at 0. This is what I'm looking for. And if you don't put a bracket around this 5, it would be confused with the power 5. So the notation is kind of, sorry, yeah. This is the power 5. This is the fifth derivative. So that's a kind of notation. So be careful about that. So I'm finding the fifth derivative at 0. So when I set these equal to these, let's see where I see the fifth derivative. I see the fifth derivative here, which is basically, I can say this is in this term. Because I'm setting these two equal to each other, the coefficient of x to the 5 here and x to the 5 here should be same. That's the only way that two things are equal to each other. Let me just come up with an example here, easier example. For example, if I have ax squared plus bx plus c is equal to 5 minus 3x squared. So here you can easily say that a is equal to -3. How? Because I just compare these two terms with each other. So I say, okay, this is x squared here. I just compare it with the x squared on the other side. So the coefficients should match. So I can say a is equal to -3. Here I have bx, and here I don't have any x. So I can say, so b is equal to 0. And here I have just one constant, which should match these 5. So c is equal to 5. So what we do, we are just matching the same degree of x with each other, those terms. And from there, we can find the coefficients. So just having this as a side note, I just put it here. I know that if I want to set these T5 with this one equal to each other, because they are actually equal to each other, I need to have this term and this term to be equal to each other, because both of them have x to the 5. That's why actually the main reason that I factored out x to the 5. It's better looking right now that you have one term with x to the 5, and here also you have one term with x to the 5. So because they are equal to each other, so I just set them equal to each other. So I just write 4 times 2 squared over 5 factorial minus 4 cubed times 2 over 3 factorial plus 4 to the power of 5 over 5 factorial x to the power of 5. This is what I get from the T5 that we kind of evaluated there. I set that equal to the fifth derivative at 0 over 5 factorial times x to the power of 5. These two are exactly the same things. So I can say, okay, because they are same, I can just cancel these two. The coefficients should match each other. They are equal to each other. So now I simply isolate the fifth derivative. So what I would get is the fifth derivative at 0 is equal to, I multiply both sides by the denominator here, by 5 factorial. So it's 5 factorial times this bracket, which let me just write it differently. This is 4 times 2 squared, which is just 4, over 5 factorial, minus, I have 4 to the power of 3. Let me see. Okay, I made a mistake here. Sorry, there was a typo here. I just quickly fixed that. So here, when I was writing that, it was a 2 factorial. My bad. So sorry about that. So this one should be also 2 factorial. And this one also should be the, oh, okay. This also should be 2 factorial. Okay. And you know, 2 factorial is just 2. So this one we have 4 to the power of 3 times 2 over 3 factorial, which is just 6. Okay. Plus 4 to the power of 5 over 5 factorial. So this is the fifth derivative. We can simplify that a little bit. So for example, 4 times 4 is 16, divided by 2 is just 8. minus, so here I can just cancel the 2 with 3, with 6, so it's 3 just here. So I get 4 to the power of 3 over 3, plus the last one, which is 4 to the power of 5 over 5 factorial, which we don't need to evaluate that. So this is already perfect form. I mean, I can again evaluate that, but it's already in the calculator ready format, which is good enough for and as answer. So I hope it was kind of clear. If there was any question, confusion, please let me know. This is the fifth derivative of the function at 0 by just comparing the short way that we got it and the long way, and we set the coefficients equal to each other. Please pause here, read the question, and see if you can solve it by yourself first. Okay, in this problem, we are asked to find all the critical points of these multivariable functions f of x and y, and then classify each of them and figure out if they are local maximum, local minimum, or a saddle point. So let's begin with defining critical point. Critical points are the points that the first derivative is 0. And because we have a multivariable function, we have partial derivatives. We take the derivative of the function with respect to x first. We have 3x squared minus 3. So basically we are assuming the y is 0. We treat y is constant, We treat y as a constant. So the derivative of that would be just 0. So I don't write anything here. And the derivative with respect to y would be, okay, we consider x as a constant. So the derivative of these would be 0. The derivative of these would be 0. And the derivative of y cubed would be 3y squared minus 6y. Now we set them equal to 0. The first one is equal to 0, which as a result we can see that 3x squared is equal to 3. So x squared is equal to 1. And as a result, x is equal to positive or negative 1. So we found two x coordinates, positive 1 and negative 1, that the first derivative with respect to x, first partial derivative with respect to x is 0. And from the second one, to set the first derivative with respect to y equal to 0, the second equation, we can factor out 3y. So what we get is y minus 2 equal to 0. So as a result, either this term is 0 or this bracket is 0. So y is equal to 0 or y is equal to 2. So we found two y coordinates. But what are the critical points? What are the coordinates of the critical points? Combination of these two. So for example, I can say when x is equal to 1 and the y is equal to 0 or y is equal to 2. So any combination there. So I can say the critical points would be -1, 0, -1, 2, +1, 0, and +1, 2. So any combination of these x and y's that I got. So now I have 4 critical points and I want to figure out if they are local maximum, local minimum, or saddle point. So what we do, we first write the formula for discriminant. Discriminant, or D, is basically fxx times fyy, the second derivative, and the second derivative with respect to x and second derivative with respect to y, minus fxy squared. So we evaluate discriminant at all of these critical points, and if d was greater than 0, and the second derivative fxx, for example, or fyy, any of them, was also greater than 0, we have a local minimum. If discriminant was greater than 0, and the second derivative fxx or fyy, doesn't matter, was less than 0, it means we are dealing with a maximum. And if d was less than 0, it means we are dealing with a saddle point. And If d was equal to 0, basically it's a very inconclusive test, which basically it does not work and we cannot make any conclusion. It doesn't mean neither. It doesn't just mean it's inconclusive. So this is how we can use the discriminant to determine if it's a maximum or minimum or saddle point. So let's just leave this here and first find fxx and fyy and fxy. So for fxx, second derivative with respect to x, I take the first derivative with respect to x. We already have that, and I take the second derivative with respect to x again. So the derivative of this with respect to x would be simply just 6x. How about fyy? Let me just write it underneath. Fyy, we take the second derivative of these with respect to y, which would be 6y minus 6. And fxy, I can write it here. I take the derivative of these with respect to y, or I take the derivative of these with respect to x. Because fxy and fyx are usually equal to each other for most of the functions that, or kind of 99% of the functions that we are dealing with would be equal to each other. Just there are some specific cases, special cases, that the functions are not nice. They call it not nice functions, which fxy and fyx would be different. So fxy would be the derivative of, for example, this one with respect to y. Because I'm taking the derivative of these with respect to y, I am treating x as a constant. And because x is a constant, this is a constant minus constant, so it's entirely 0. And if I take the derivative of this with respect to x, I see that's again 0. So the second derivative would be 0. Now I can just set up my discriminant. Discriminant is basically fxx, or basically 6x, multiplied by 6y minus 6 minus 0. So what I have here is fxx. I just write it here. And this is fyy. Perfect. Now I evaluate that at all of these points. So what I do, I just create a table here. So the points are -1, 0, -1, 2, +1, 0, and +1, 2. And I find the discriminant for all of them here. Discriminant, which is kind of 6x minus 6x times 6y minus 6. And what we care at this point is whether they are positive, or whether it is positive or negative. So if I plug in -1 and 0, what happens? I plug in -1 for x, I plug in 0 for y. Overall, what I get is -6 times a negative bracket, -6, so it's positive. If I plug in this one, -1 and 2, I get negative and positive, overall negative. If I plug in this one, I get positive and negative, which is negative, and I plug this one, I get positive and positive, which gives me positive. And we said, if it is negative, we have a saddle point. So at this point and this point, these two critical points, we have saddle point. But how about these two? For these two, there is a condition. Because if they are positive, it depends on the sign of fxx or fyy. So what we do, we also check fxx. So fxx, at this point, I just write another, create another column here, fxx. I evaluate fxx at this point, which is just 6 times the x coordinate, which is just negative. And at the other one, it would be positive. Because the discriminant is positive and fxx is negative, I'm dealing with this one, which means I have a maximum. I just write the local max. And this one, because it's positive and the second derivative of fxx is also positive, this case, which I have a minimum. So I have a local minimum. So I can just say that here I have max, saddle, saddle, and mean. So these are basically the classification of these critical points.